Hey, what's up? This is Mark at Alchemist.camp, where we learn Elixir and Phoenix by building things. And today, the top requested thing to be built, or to be taught in this case, is a TDD series, or test-driven development. So, we're going to start a new series on testing, and the very first lesson of it is going to be TDD. If you're not familiar with TDD at all, I'll give you a quick overview. And quick disclaimer, I have never worked at some place like Pivotal Labs or one of those consultancies where everything is TDD'd all the time. I've done some TDD and I've encountered it a lot in interviews, but if you're really deep into TDD and believe there's something that I missed that I should have covered or have any comments, well, I will accept them as humbly as possible. So here's the basic idea. You start by writing a test that fails, and it fails because it's testing for some functionality that you haven't implemented yet. Then you write the code to implement that functionality up to the point that it gets the previous test passing. Then you may or may not need to refactor your code. Then you write another test, which is also failing, and the reason is because that's for something else that isn't implemented yet. You write the code you need to get it passing, and if necessary, refactor it, make sure all your tests are still passing, and then just go around and around in this loop. Writing your code this way has some advantages. One big one is that you're writing your tests first, which means you're not going to be as likely to have a blind spot where you've already written something and then you test it based on your experience of what you've just done writing it, and you very possibly don't test the very thing that's broken about it because it's not at the top of your mind. The other thing is, if you work this way, you'll also get a lot of test coverage. Like, you'll have very near 100% test coverage. So with that said, let's get started. We'll go to a new terminal and we'll create a new project. It's not a Phoenix project, it's just a plain Elixir mix project. So mix new Fibonacci. We're going to make a Fibonacci number calculator. Fibonacci. And now that it's created, we'll cd into it and we'll run the tests as it suggests. Mix test. Everything passed, and let's see what we tested exactly and what the files are. So in our new mix project, we have a lib with a Fibonacci file. So it's got a module doc at the top and a doc block for the hello function with an example. This example is actually called a mix test, and that runs every single time you run mix test. So that's why we see one doc test. The output of Fibonacci.hello is world, and that's because we have a file here, or we have a function here, hello, which returns world. Now let's have a look inside our test directory. So we have a test helper, which starts ExUnit. ExUnit is the name of the library that's built into Elixir that's used for unit testing. Then we have a Fibonacci test.exs file. Notice that this name is the same name as the file that it's testing with an underscore test appended to it. That is the common pattern, and you can test any file in your project by following that naming convention. And also note that it's an exs file as opposed to an ex file. That just means it's a script. All right, so inside our Fibonacci test module, we've got use exunit.case. That brings in functionality using a macro. And then we also have doc test Fibonacci. Our test here simply asserts that Fibonacci.hello returns the atom world. So it's basically the same test as what's in the doc test. Let's just get rid of this because we don't want that test anymore. And we'll make our own test. And we'll say the first Fibonacci number is 1. And inside our test, we'll assert that Fibonacci.nth, which is a function we haven't made yet, will return 1 for the first Fibonacci. And we'll save that. And let's also get rid of the bogus hello stuff that we've got in our module. Let's see, we'll make this documentation change to reflect the real world as well. So calculates numbers from the Fibonacci sequence. And Fibonacci.nth is going to return 1 if n is 1. Okay, so we haven't written the code, but we do have a test. We also have a doc test, which is the exact same thing. Run mix test, and now we have one test, one failure. Test the first Fibonacci number is 1, and it's just an undefined function error. So let's fix that. The simplest way to fix this, make this a bit higher and close it like that. All right. The simplest way to fix this is we'll define a new function, and we'll make it very simple, just a one-liner called nth. And when we pass nth 1, we return 1, since the first Fibonacci number is 1. And by the way, if you're not familiar with Fibonacci numbers, that's the sequence that goes 1, 1, 2, 3, 5, 8, 13, 21. It's very famous, and basically each number is just the sum of the two before it. So 1 plus 1 is 2, 1 plus 2 is 3, and so on. So we're going to run our test now and see if it passes. All right, so now it's green. Next thing to do is we'll go back to our test and we'll add one for the next Fibonacci number. The next Fibonacci number would be the second. The second Fibonacci number is also 1, actually. And our test fails. We have 2 tests, 1 failure. So we expected 1, but we got 2. Well, that's not what we wanted. So let's fix that. And we can just say for any n, it's always going to be 1. So nth of n is going to be 1. Now we're green again, so we'll go back to our tests. And the next thing we'll test is the third number. This is a little bit tedious, but actually you do want to test the base case of any sort of iteratively generated sequence like this. So the base case is actually just numbers 1 and 2, and then we need to test the progression as well. So the third Fibonacci number is going to be 2. Our test is failing. We can see it should have been 2, but we thought it was 1 because our function is very stupid. It just says the answer for all of them is n. So the second Fibonacci number is 2. Now, every Fibonacci number after 1 and 2 is going to be the previous 2 combined. So it's a very simple way to do this. We can just recursively say for every n, the Fibonacci number is the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. So in other words, the third Fibonacci number is the second Fibonacci number plus the first Fibonacci number, or the 100th would be the 99th plus the 98th. Our tests are passing now. So we can add a couple more, but they're probably not going to be any problems since we've tested all the base cases. So the fourth Fibonacci number should be 3. The fourth is 3. The fifth Fibonacci number is going to be 5. And I guess we'll do one more. The sixth Fibonacci number is going to be 3 plus 5, so that'll be 8. Our tests are still passing. So what else do we need to test about our Fibonacci numbers? Well, one thing that is probably a good idea is we want to test to make sure the algorithm we're using is reasonable. So as I just said, this is a generative sort of solution, or it's a generative sequence. So by its definition, we know that the 100th Fibonacci number is going to be the 99th Fibonacci number plus the 98th Fibonacci number. Let's make a test for that. And we're going to just test that it doesn't take too long. Shouldn't take too long. And the way we'll test that is by asserting that the 100th Fibonacci number is the 99th plus the 98th. All right, we'll run that test. Whoops, that was a mistake here. Failed for line 30. Assert Fibonacci.nth equals Fibonacci, dot nth and dot nth. Okay, we have a problem. Not only is this taking way too long, but we don't even finish the tests because it's just running the test and running it and running it and running it. There is a default for when tests will time out. The default is set pretty high though. The default is, I believe it's a full minute. Fortunately, there's something we can do, which is we can set a tag with a timeout. So we can say tag and then timeout, and we'll specify how many milliseconds we're allowed to run the test. We'll say this has to run within 1,000 milliseconds or 1 second, or else it times out. We'll run mixed test now. After 1 second, it fails. Timeout error, test timed out after 100 milliseconds. You can change the timeout with tag and timeout of X, which we just did, or module tag with timeout to set it for every case. And let's actually do that because just it's more rigorous, I think, to make sure that none of our calculations take that long. So we'll go up here. Module tag, actually not doc. Module tag of timeout 1 second. And we have the same failure that we had before. All right, so we're still red. So how do we fix this? Let's take a look at our Fibonacci algorithm. What is the big O of this? Well, for any number n, we're going to be calling this nth function once for n-1 and once for n-2. Now, on n-1, we're also going to be calling n-2, and we'll be calling n-3. For n-2, which we're calling twice because of this time and for the n-1th time, for n-2, we're going to be calling 2 other nths. So we can be sure that for every 2 numbers of n, every time n increases by 2, we're more than doubling the number of times that we call the function. And that's pretty bad. That's actually exponential time complexity. So no wonder it goes crazy with just 100, because we've just shown that it's worse than 2 to the n over 2 power. So 2 to the 50th power. Now keep in mind, we know 2 to the 10th is 1024, which is about 1,000 or 10 to the 3rd. So for every 2 to the 10, that's adding more than 10 to the 3rd. So more than 3 zeros. So 2 to the 50th, well, that's 15 zeros after some number. So we've got a gigantic number of times that we're running this function just to calculate the 100th Fibonacci number. What one would normally do in an imperative language would be just to rewrite this and use a loop and just loop through the Fibonacci numbers, adding them up and keeping track of the previous two. So we could say the previous two added together is the next one, then these two added together is the next one, and so on. Elixir is functional and it's immutable, so that lends itself better to using recursion, but we'll rewrite this so that we have accumulators, and we'll basically do that same process as you would do with a loop. So we'll have the same function, nth, and when we call nth, we will, instead of returning a number directly, we'll call another version of nth that has two accumulators, and call nth with n and a 0 and a 1, and this will make more sense in a couple minutes. Then the other version of our function, nth, has accumulator 1 and an accumulator number 2. And what this will return is calling itself with n-1 and accumulator 2. So whatever was in accumulator 2 basically moves to the accumulator 1 position. And then the new accumulator 2 is accumulator 1 plus accumulator 2. Let's go through this just to make sure that it makes sense. We have, I'm just going to put it inside a multi-line string here. So if we were to call this nth with n equal to 5, first time we call it, we'll have n is 5, and that, or actually, wait a second, I think we want n-1, and that's because the first two Fibonacci numbers are both 1. So the first time we call this with n equal to 5 is we'll have called it with n-1, so we'll have 4, and then 0 in our accumulator 1 position, and 1 in our accumulator 2 position. Next time through, we'll have 3, because it's n-1, then accumulator number 2 moves into the accumulator number 1 position, so this is here, and then the accumulator number 2 is the sum of these two numbers, so that's 1. The next time we go through the loop, n is going to be 2, and then this 1 will move into the accumulator 1 position. Then accumulator 2 is going to be the previous accumulators 1 and 2 added together. 1 plus 1 is 2. The next time we go through, n will be 1. We'll have accumulator 2, the value 2, moved into accumulator 1, and the new accumulator 2 is going to be 1 plus 2, which is 3. Then the next time through, n will be 0, accumulator 1 will be 3, accumulator 2 will be 2 plus 3, or 5. And once we get down to this case, we'll just return accumulator 2. So nth of 0, accumulator 1, which we're not going to use, and accumulator 2, we return accumulator 2. So as you can see, this is basically doing the same thing. You can see this accumulator 2 is exactly tracking what the Fibonacci sequence does. Actually, so is accumulator 1, but just one step behind. Now remember the original functions we wrote to calculate the Fibonacci number. Every 2 higher n got, we called the function at least twice as many times, because n itself would call n-2 to calculate itself, and then n-1 would also call that previous Fibonacci number to calculate itself. So it was just this crazy exponential explosion. But in this case, if n were equal to 7, we wouldn't double the number of times we call the function. We're calling it 5 times here. If n were equal to 7, then the first iteration we would have 6, and 0 and 1. The second time through, we'd have 6, 1, and 1. The third, or we'd have 5, 1, and 1. The third time through, we'd have 4, 1, and 2. The next time through, we'd have a 2 over here, and we'd have a 3. Next time through, we'd have a 3 and a 5. And then the next time, we'd have 1, 5, 8. And then the last time through, we would have 0, 8, and 13. So we'd only call the function one time for each number n. So this function is no longer exponential time complexity. It's just linear, except when the result gets so gigantic that it takes up a ridiculous amount of memory. But we're not going to worry about that for the moment. We'll save it and then see if we can get to green. And there's a missing do in option def. All right, let's have a look at that. Looks like I wiped out a character there at some point. All right, 7 tests, 0 failures. Let's go back to our tests. Now that we have a working function that's tested, let's look at our overview again. We have test passing. We did some refactoring. Let's make a failing test now. And this test will be for a function we haven't written yet that will get the first n Fibonacci numbers. Before we do that, let's add a little bit of structure with a describe. Describe works pretty much the same as it does in other testing frameworks for other languages. It's just a block that we can put other tests under. So this whole first block that we've done will be called calculate the nth Fibonacci number. And we'll pull this end down to the bottom of the tests that we've already written. And finally, let's get rid of Fibonacci from all of these. It's a little bit redundant. Okay, so that's our first describe block. Our second one will be for the other function we're about to make. Let me scroll up a bit here. Describe, calculate the first n Fibonacci numbers. And the first test will be for when we ask for 0. Doesn't return any for 0. And why don't we have an end there? All right. Refute enum.count. And that just gets a length of a list. We'll refute that the count of Fibonacci.first n is greater than 0. Next test, and we have an undefined function error, just as we expected. So let's make that function. First n for 0, we'll just return an empty list. First n Fibonacci number doesn't return any for 0. Fibonacci first n, undefined or private. Oh, because we didn't pass it any arguments. First n of 0. And now it passes. This is a little bit silly though. Refute, I'm just showing refute here is the opposite of what assert does, but refuting that the length is not more than 0 is actually telling us less than if we just assert that we get back an empty list. Okay, so refactored that test. Let's make another test to break things. Returns the first number for 1. First n of 1, it should be, first Fibonacci number is just 1. We're red, so we'll go in there and add a case for the first one. Now it's green. And we've already tested 0, already tested 1. That's really the base case. So actually we'll do one more for 2. Returns the first 2. For 2, actually that's a little bit unclear. Returns 2, returns the first 2 numbers. And it's going to look like that. And we've got one failure because nothing matches. We're only matching on 0 and 1. Okay, so that truly does cover the base cases. Next, let's add something that forces us to make a more reasonable function than just doing things one possible input at a time. So 6 will return the first 6 numbers, and 6, let's see, 1, 1, 2, 3, 5, and 8 are the first 6 Fibonacci numbers. That fails, as it should. Okay, so let's think about how to do this. We want to get a list that has the first n Fibonacci numbers. Well, since we've already got a function that calculates the nth, we can just do a comprehension here. We'll just do for I generated from 1 to n, do nth of I. And that should actually do it. Yep, okay, so we've got 11 tests, 11 failures. What's the next thing? Well, we could test some bad input and assert that it throws an error, that sort of thing. I'm going to hold off for that till next episode when we do some Phoenix testing. Instead, we're going to test something related to speed again, because this is actually not an ideal algorithm. Test that 10,000 isn't too slow. And the way we'll do that is we'll first get the first 9,999. So first, actually we'll just get the first 10,000. First 10K is Fibonacci.first n of 10,000. Then we'll assert that first 10,001 is equal to the nth of 10,001. So the first 10,001 is going to be the same thing as the first 10,000, except we're also going to have the next number added onto it. So it's going to be the same as first 10K appended with Fibonacci.nth, and this is not that efficient. Remember, lists are easy to add things to the beginning to, but in order to add something to the end of them, you have to traverse the entire list. Doing this one time in a test is not a big deal though. So try that, and wait a minute, I didn't save it. There we go. This should time out. Oh, could not invoke it in a match. It should be equals, not, should be a test for equality, not a match or an assignment. Okay, and we timed out. And if we were to set the amount of time allowed up, I don't know, probably 10 or 15 seconds, this would work. But let's see what the problem is. So it's clearly much faster than it was initially for the first n when we had it failing on just going to 100. We're not at exponential time, but in order to get the first n, we're getting the nth one n times. So this is roughly an n squared time complexity, and we can do better than that. So the way we'll deal with this is we'll go back to our previous implementation we had a moment ago. And let's open up IEX and just have a look at how lists work again. This is probably nothing new for any of you, but so we've got a list that's got the elements 1, 2, and 3, and we could match the head and tail of that list. And now the head is 1, and the tail is a list containing 2 and 3. And same thing we can do with the tail. So matching the head and the tail from the tail. Now the head is 2. The tail is a list containing 3. And we could do that again. And now the head is 3. And the tail is an empty list. So lists are built up in this kind of fashion. We'll have the first thing and then a list containing all the other things. And it's just going to be lists all the way down like so. Oops. And that just gets printed as 1, 2, 3, 4 because it's a lot easier to recognize in this. But we can use this for pattern matching, and we're going to do exactly that. Just like we did with the nth function, we're going to make one version, which will be the entry point, so first n, and it's just going to take a single argument of n, and then that's going to call out another version with an accumulator. So first n, and this one will take the n and we'll pass it an empty list, and the list is where we'll accumulate our result. If we receive an n and an empty list, then we're going to do first n with n minus 1 and just a 1, since that's the first thing. So n will be decrementing from whatever n is down to 0, but we'll be building up the list from 1 because the distance from n to 0 is the same as from 0 to n. Then the next case is if we get a list containing just a 1, we'll still call first of n on n minus 1, and we'll have a list containing 1, 1. Remember, that's the exact same thing as this, because it's just a linked list, or a cons if you're from Lisp. The next, actually after that, that's enough till we can do the general case. So we'll get n, and then we'll have some list, which will have a first element, and then it will have a list, which has at the head of it a second element, and whatever else is in the list. That's just the tail. In the case that we have a list with 1 and 1, E1, element 1 would be 1, element 2 would be 1, and the tail would just be an empty list. So we want to call first n again, once again decrementing n, and then the list is going to be element 1 plus element 2, because that's going to be the next Fibonacci number, and then whatever was in the entire list. So let's match this here as accumulator. In fact, let's make this not be a single line function. Accumulator. So we've basically got whatever the next Fibonacci number is, followed by the rest of the list. The reason this isn't wrapped in brackets is because it already is a list. It's not just a bare number. And we'll have another look. Tail is unused. Is that right? Actually, that is right. Don't need to match tail. Run it again. Okay, no warnings. And Fibonacci dot first n of 3 never stops. That's not a good sign. Let's see. Oh, we do still need to handle the 0 case. So once n gets down to 0, then we just return the accumulator. And actually, that's not quite right, but I'll do it this way first so we can see it. N and 0, sorry, 0 and whatever the accumulator, just return the accumulator. Okay, so basically we go through our list, and every iteration we take 1 off of n, and we add up the first 2 elements to make a new element that we put in front of the elements we've already built up until we get to 0, and then we just return the list of all the things. Okay, Fibonacci first 3, first 5, first 15. Looks pretty good, except that we've got everything backwards. You might wonder why we weren't just building it up like this. And the answer to that is because, as I said, when you're adding to the end of a list, since it is a linked list, since it is this kind of structure, in order to add another element, we actually have to traverse the entire list until we get to the very end of it before we can add it. On the other hand, if we have an already existing list of this, in order to add an element to the front, it's very fast because we're just taking all of this in actually, we're not even moving anything. We're just creating a new element with the value of 2, and then it points to this list that we've already built up. And then the next element will be a 3 that points to this current list. So it's very fast to build them up from the beginning. Close that, and the final step is enum.reverse the accumulator. In any case, let's run our tests, since that is our golden standard, see if they are or aren't green. It's kind of hard to see what went wrong here. So let's fire up IEX with mix. And we'll do Fibonacci. Actually, we'll say first 10 is equal to Fibonacci dot first n 10. Actually, let's look at our test here. So we just looked at the first 10K Fibonacci numbers and appended the 10,000 first one to it. So let's just do a simple test with 10 of them. So we'll say first 10 is equal to Fibonacci dot first n of 10. So first 10 append Fibonacci dot nth 11. Okay, here it's pretty clear what happened. If you're familiar with what lists look like in the terminal. So notice after 55, we don't have a comma, but instead we have a vertical bar. So that represents the cells that I was showing you when we were building up the list. So 1, 1 is actually the same thing as 1 vertical bar 1, like that. Or 1, 2, or 1, 1, 2 is the same as that. So this 55 is actually, this 5589 is kind of like if we just saw this instead of it being an empty list. So what we need is another empty list here. Basically 89 should have been wrapped in a list. If we do this, now we'll have an actual list with a proper end. The very last element in a list is always an empty list. All right, so we'll just wrap those brackets there, and we should be able to mix test and get everything to pass. And it's actually considerably faster. I believe if we do like a Fibonacci first n of 100,000, it's still not going to take that long. That was a little bit. All right. So that is a basic taste of test-driven development. This was obviously a very simple problem, but you can see how we just built up one test at a time and did what we needed to in order to fix the failing tests. And in the end, we have a refactored version of our function, and as we went through it, we built up a reasonable set of tests. So obviously we didn't test everything we could have about it, but you kind of get the idea. There are a lot of things that ExUnit can do besides just assert and refute. It's actually my favorite unit testing library I've ever used, and I've used some pretty decent ones, I would say. And in the docs, you can see all the functions that the library has. In general, you'll probably be using assert the most, as we were. Refute is also pretty common. And assert received if you're dealing with processes or anything async. And we also have in deltas, refute in delta, assert in delta if we want to check that something is within a certain delta of another thing. And finally, catching errors and catching exits is relatively common. There are also quite a few tags besides the timeout that we used. I generally haven't gone too deep into all the things that we get from ExUnit because there's so much that you can do with just asserting and pattern matching. One other thing worth pointing out is that we don't generally do a lot of mocks in Elixir. And the reason for that is because everything's immutable and there's so much pattern matching. If you wanted to test if a user were logged in, or if you wanted to mock a logged in user, it's actually easier to just pass in whatever struct would be, say you're doing a Phoenix app, whatever struct would be in the con, or whatever shape you're expecting. So maybe you're matching something inside the con assigns to see if a user is logged in. And if that matches in the function head, you expect a certain behavior to happen, and you can just put that in your tests. And we'll be looking more into that next episode when we do some testing with Phoenix. That's it for this time. So if you found the episode useful, then definitely subscribe, click the bell so you get more like it, and see you next time.